The degree of a polynomial is one of its most fundamental characteristics. It tells us the highest power of the variable in the entire expression and helps us classify and understand the polynomial's behavior. Let's examine our first example. Consider the polynomial x to the fourth power minus 4x cubed minus 2x squared minus 5x plus 9. To find the degree, we need to identify which term has the highest exponent. Let's examine each term systematically. The first term is x to the fourth power, which has an exponent of 4. The second term is negative 4x cubed, with an exponent of 3. The third term is negative 2x squared with degree 2. The fourth term is negative 5x with degree 1. And the constant term 9 has degree 0 since it contains no variable. Since the highest exponent among all terms is 4, the degree of this entire polynomial is 4. We highlight the term with the highest power to clearly identify the polynomial's degree. Polynomials are classified by their degree, and each classification has a specific name. Let's explore these classifications with examples to understand how degree determines the polynomial's category. A polynomial of degree 0 is called a constant polynomial, such as 7. A polynomial of degree 1 is linear, like 3x plus 2. Degree 2 polynomials are quadratic, such as x squared minus 4x plus 3. Continuing with higher degrees, degree 3 polynomials are cubic, like 2x cubed minus x squared plus 5. Degree 4 polynomials are quartic, and degree 5 polynomials are quintic. Beyond degree 5, we typically just refer to them by their numerical degree. Let's practice identifying degrees with more examples. Consider the polynomial 5x cubed plus 2x minus 8. What is its degree? Looking at each term, 5x cubed has degree 3, 2x has degree 1, and negative 8 has degree 0. The highest degree is 3, so this is a cubic polynomial with degree 3. Here's another example. 7x to the sixth power minus 3x to the fourth power plus x squared minus 10. Can you identify the degree? The terms have degrees 6, 4, 2, and 0 respectively. The highest degree is 6, making this a sixth degree polynomial. Notice how we always look for the term with the largest exponent. Understanding polynomial degree is crucial because it determines many important properties. The degree tells us the maximum number of roots the polynomial can have, the general shape of its graph, and how it behaves for very large values of the variable. In summary, the degree of a polynomial is simply the highest exponent of the variable. This single number tells us the polynomial's classification, helps predict its behavior, and is fundamental to understanding polynomial operations. Always remember to examine every term and identify the one with the largest exponent. Standard form is a specific way of writing polynomials that makes them easier to work with and compare. Understanding this format is essential for polynomial operations. In standard form, we arrange polynomial terms in descending order of their degrees. This means the term with the highest power comes first, followed by terms with decreasing powers. Here we have a polynomial with terms arranged randomly. 4x plus 15 minus 2x squared plus 4x cubed. Notice how the terms are not organized by their degrees. Let's identify the degree of each term. The term 4x has degree 1, the constant 15 has degree 0, negative 2x squared has degree 2, and 4x cubed has degree 3. To write this in standard form, we rearrange the terms in descending order of degree. We start with the highest degree term and work our way down. First, we place the term with degree 3, which is 4x cubed. Next comes the degree 2 term, negative 2x squared, then the degree 1 term, positive 4x. Finally, the constant term 15 with degree 0. The standard form is 4x cubed minus 2x squared plus 4x plus 15. Notice how the degrees decrease from left to right, 3, 2, 1, 0. Writing polynomials in standard form provides several important benefits. It makes polynomials easier to compare, simplifies mathematical operations, and allows us to immediately identify the degree of the polynomial. Remember, standard form arranges terms from highest degree to lowest degree. This consistent format is the foundation for all polynomial operations and makes working with polynomials much more systematic and organized. Adding polynomials is a fundamental algebraic operation that involves combining like terms to create a simplified expression. Understanding this process is essential for working with polynomial expressions in mathematics. The basic principle of adding polynomials is straightforward. We can only combine terms that have identical variables raised to identical exponents. These are called like terms. Let's examine two polynomials to understand this process. Here we have our first polynomial, 3x squared plus 5x plus 7, and our second polynomial, 2x squared minus 3x plus 4. To add these polynomials, we first identify the like terms. Like terms have the same variable raised to the same power. Let's highlight the x squared terms in blue. Next, we identify the x terms, which we'll highlight in a different shade of blue. Finally, we identify the constant terms, numbers without variables, which we'll highlight in a lighter blue. Now we combine the coefficients of like terms. For the x squared terms, 3 plus 2 equals 5. For the x terms, 5 minus 3 equals 2. For the constants, 7 plus 4 equals 11. The final result combines all these simplified terms into one polynomial. Our answer is 5x squared plus 2x plus 11. This is the simplified form of adding our original two polynomials. This process of identifying like terms and combining their coefficients is the foundation of polynomial addition. In the following sections, we will break down this process into detailed steps and explore various methods for adding polynomials efficiently. The first crucial step in adding polynomials is identifying like terms. Like terms are terms that contain the same variable raised to exactly the same power. Like terms are defined as terms that have the same variable raised to the same power. Only the coefficients can be different between like terms. Let's break down our polynomial addition problem into individual terms from each polynomial so we can systematically identify which terms are alike. Let's identify our first pair of like terms. We have 4x cubed from the first polynomial and negative 8x cubed from the second polynomial. Both terms have the variable x raised to the third power, making them like terms. Next, we identify another pair of like terms. We have 4x from the first polynomial and negative 9x from the second polynomial. Both terms contain the variable x raised to the first power, so they are like terms. We also have constant terms, positive 15 from the first polynomial and negative 6 from the second polynomial. Constant terms are like terms because they have no variables, or we can think of them as having x raised to the 0 power. It's equally important to recognize terms that are not like terms. For example, x to the fourth power and negative 2x squared are not like terms because they have different exponents. Similarly, x cubed and x squared have different powers, so they cannot be combined. To summarize our identification process, we found three pairs of like terms in our polynomial addition problem. The x cubed terms, the x terms, and the constant terms can each be combined because they have matching variables and exponents. We will work through a detailed example of adding two polynomials. Our task is to add the polynomial 4x cubed minus 2x squared plus 4x plus 15 to the polynomial x to the fourth minus 8x cubed minus 9x minus 6. The first step in adding polynomials is to identify like terms. Like terms have the same variable raised to the same power. Let's examine each term carefully and group them by their degree. Let me break down each polynomial into its individual terms so we can clearly see what we're working with. The first polynomial contains 4x cubed, negative 2x squared, positive 4x, and positive 15. The second polynomial contains x to the fourth, negative 8x cubed, negative 9x, and negative 6. Now we can clearly identify which terms can be combined together. Now let's systematically identify like terms by organizing them according to their degree. We'll start with the highest degree and work our way down. For degree 4 terms, we only have x to the fourth from the second polynomial. There's no corresponding term in the first polynomial, so this term remains unchanged. For degree 3 terms, we have 4x cubed from the first polynomial and negative 8x cubed from the second polynomial. These are like terms because they both have x raised to the third power. For degree 2 terms, we only have negative 2x squared from the first polynomial. Since there's no corresponding x squared term in the second polynomial, this term remains as negative 2x squared. For degree 1 terms, we have positive 4x from the first polynomial and negative 9x from the second polynomial. These are like terms since they both contain x to the first power. Finally, for degree 0 terms, which are the constant terms, we have positive 15 from the first polynomial and negative 6 from the second polynomial. These are like terms because they're both constants. Now let's clear our work area and write out the final simplified polynomial by combining all our results in standard form, from highest degree to lowest degree. The final simplified polynomial is x to the fourth minus 4x cubed minus 2x squared minus 5x plus 9. Notice how we've arranged the terms in standard form with degrees decreasing from left to right. This systematic approach of identifying like terms, combining their coefficients, and arranging the result in standard form ensures accuracy when adding polynomials. The key is to be methodical and careful with signs and coefficients. Consider a practical scenario where you work two part-time jobs. Understanding how to add polynomials helps you calculate your total earnings from multiple income sources. Your waitstaff position pays a base amount plus tips per hour worked, while your cashier position pays a straight hourly wage. Each job's pay can be represented as a polynomial expression. Let's examine the mathematical expressions for each job's pay structure. The waitstaff pay is represented by 5.50h plus $50, where h represents hours worked. The $50 is a base amount, and $5.50 is earned per hour in tips. The cashier pay is simply $9.50h, representing $9.50 per hour worked with no base pay. In both expressions, h represents the variable for hours worked. This allows us to calculate pay for any number of hours. To find your total pay from both jobs, we need to add these two polynomial expressions together. We set up the addition by placing the waitstaff polynomial in parentheses and adding the cashier polynomial. First, we identify the like terms. Like terms have the same variable raised to the same power. The like terms are 5.50h and 9.50h, both containing the variable h to the first power. Next, we combine the like terms by adding their coefficients. 5.50 plus 9.50 equals 15. The coefficient calculation shows that 5.50 plus 9.50 equals 15. The final result is 15h plus 50, representing your total pay from both jobs. This result tells us that your combined hourly rate is $15 per hour, plus you receive a $50 base amount from the waitstaff position. For example, working 8 hours would earn you $170 total. This real-world application demonstrates how polynomial addition helps solve practical problems involving multiple income sources or any situation where you need to combine linear relationships. When subtracting polynomials, the key step is to distribute the negative sign to every term in the second polynomial before combining like terms. This process transforms subtraction into addition, making the calculation much more manageable. The fundamental principle is straightforward. To subtract one polynomial from another, we distribute the negative sign to each term in the second polynomial, then proceed with standard polynomial addition. Let's work through a specific example. We need to subtract the polynomial 3x squared plus 2x minus 1 from 5x squared minus x plus 4. First, we identify the subtraction sign and the second polynomial that needs to have the negative sign distributed to each of its terms. Step 1. We distribute the negative sign to each term in the second polynomial. The positive 3x squared becomes negative 3x squared, the positive 2x becomes negative 2x, and the negative 1 becomes positive 1. Notice how each term in the second polynomial has changed sign. 3x squared became negative 3x squared, 2x became negative 2x, and negative 1 became positive 1. Step 2. Now we group the like terms together. We have x squared terms, x terms, and constant terms that can be combined. The x squared terms are grouped together, the x terms are grouped together, and the constant terms are grouped together. Each group can now be simplified by combining coefficients. Step 3. We combine the coefficients within each group. 5 minus 3 equals 2 for the x squared terms, negative 1 minus 2 equals negative 3 for the x terms, and 4 plus 1 equals 5 for the constants. The final simplified answer is 2x squared minus 3x plus 5. This demonstrates how distributing the negative sign transforms polynomial subtraction into a straightforward addition problem. Remember, the key to successful polynomial subtraction is careful distribution of the negative sign to every term in the second polynomial, followed by systematic combination of like terms. This systematic approach ensures accuracy and helps avoid common sign errors that often occur in polynomial subtraction. The vertical alignment method is a powerful technique for adding polynomials that significantly reduces errors and improves organization. By writing polynomials one above the other and aligning like terms in columns, we can systematically combine coefficients while maintaining clear visual structure. Let's start with two polynomials written in the traditional horizontal format. We have our first polynomial, 3x cubed plus 2x squared minus 5x plus 7, and our second polynomial, x cubed minus 4x squared plus 3x minus 2. Now we'll apply the vertical alignment method. The key is to write the polynomials one above the other, ensuring that terms with the same degree are aligned in the same column. We align the cubic terms in the first column, the quadratic terms in the second column, the linear terms in the third column, and the constant terms in the fourth column. Notice how each column contains terms of the same degree. Let's highlight the cubic terms column. Both 3x cubed and x cubed are perfectly aligned, making it easy to see that we need to add their coefficients, 3 plus 1. Next, the quadratic terms column shows 2x squared and negative 4x squared aligned vertically. The vertical alignment makes it clear we're combining 2 plus negative 4. Now we add the coefficients in each column systematically. The vertical alignment ensures we never accidentally combine unlike terms, which is one of the most common errors in polynomial addition. Working from left to right, 3x cubed plus x cubed equals 4x cubed. 2x squared minus 4x squared equals negative 2x squared. Negative 5x plus 3x equals negative 2x, and 7 minus 2 equals 5. The vertical alignment method offers several key advantages. It prevents the common mistake of combining unlike terms because the visual structure makes it impossible to accidentally add terms from different columns. It makes coefficient addition much clearer by isolating the numerical operations. This systematic approach significantly reduces arithmetic errors and provides excellent visual organization for complex polynomials. Master the vertical alignment method through consistent practice. Start with simpler polynomials and gradually work up to more complex expressions. This technique will become second nature and dramatically improve your accuracy in polynomial operations. Polynomial addition becomes much more meaningful when we connect it to real-world scenarios. Mathematical concepts gain practical significance when students can see how they apply to everyday situations, business decisions, and scientific calculations. Let's start with a business scenario. A manufacturing company has two types of costs: fixed costs that don't change with production volume, and variable costs that increase with each unit produced. Both can be modeled using polynomials. To find the total cost function, we add these two polynomials together. This gives us a complete picture of all manufacturing expenses as a function of production volume x. In physics, polynomial addition helps us analyze motion. Consider an object with initial position and velocity, subject to constant acceleration. The position function combines multiple polynomial terms representing different aspects of motion. The total position function is found by adding these polynomial components. This gives us a complete equation that describes the object's position at any time t, incorporating all aspects of its motion. Engineering applications frequently involve combining multiple design constraints. For example, when calculating the total load on a structural beam, engineers must add polynomials representing different types of forces and stresses. The total load function combines all these individual load polynomials. Engineers use this comprehensive function to ensure the structural design can safely handle all expected forces throughout the beam's length. In economics, polynomial addition helps model complex market relationships. Supply and demand functions often involve multiple factors that can be represented as separate polynomial terms, which are then combined to analyze market equilibrium. The total supply function combines both base supply and seasonal adjustments. This comprehensive model allows economists to predict market behavior more accurately by accounting for multiple influencing factors simultaneously. These real-world applications demonstrate why polynomial addition is such a fundamental mathematical skill. Whether analyzing business costs, predicting physical motion, designing structures, or modeling economic systems, the ability to combine polynomial expressions provides powerful tools for understanding and solving complex problems. Modern technology has revolutionized how students learn polynomial addition. Online tools and interactive platforms provide powerful resources that enhance understanding through immediate feedback and visual manipulation. Digital polynomial tools offer numerous advantages over traditional paper and pencil methods. They provide immediate feedback, show step-by-step solutions, create visual representations, enable interactive practice, and automatically detect common errors. When students click the Add button, these calculators instantly display the result. The polynomial 3x squared plus 2x minus 5 added to x squared minus 4x plus 7 equals 4x squared minus 2x plus 2. Beyond simple calculators, interactive platforms offer comprehensive learning environments. These platforms provide guided tutorials, practice exercises, and visual demonstrations that help students understand the underlying concepts. Interactive platforms break down polynomial addition into clear, manageable steps. Students can see each phase of the process, from identifying like terms to writing the final answer in standard form. Various types of technology tools are available for polynomial learning. These include web-based calculators, mobile applications, interactive websites, and comprehensive learning management systems. Web-based calculators provide instant computation, mobile apps offer learning on the go, interactive websites feature engaging exercises, and learning management systems deliver comprehensive courses with progress tracking. The most effective digital tools share three key features. First, they provide instant feedback with immediate error detection and correction guidance. Second, they use visual learning techniques with color-coded terms and animated solutions. Third, they offer unlimited practice exercises with varying difficulty levels to build mastery. Technology integration transforms polynomial learning from a static, paper-based process into a dynamic, interactive experience. These digital tools not only make learning more engaging, but also provide personalized feedback that helps students master polynomial addition more effectively than traditional methods alone.